Hello students, welcome back. Previously we just completed this problem. We went through the plotting and determined its domain. Now let's go to the next problem. This time, ball is in your court. Stop the playback and complete the problem. All done? Maybe not? Well, in any case, let's go. You can always stop the playback and go back to your problem. Okay, here is the graphing calculator, and y equals 2, and the numerator 2x to the 4th power minus 7x to the 3rd power plus x minus 1 divided by the denominator x squared minus x plus 3. Okay, here we go. We have this graph. This is very different from the kind of graph you saw before. Previously, we had some horizontal and vertical linear structure, but nothing here. Everything is just curved. Even if I zoom out, nothing linear. Actually, if I zoom out sufficiently, it looks like a parabola. That's another type of graph. Okay, we're going to talk about those asymptotes a little bit later because that's a little bit bigger topic, and we're going to cover those asymptotes in sections 2, 3, and 4. For now, let's stick to domain. Okay, how many curved P's do you see? I see just one. Even if I zoom out, just one. And then to the right or to the left, they are going to go on forever actually. You see, it's not stopping like this. Going to the boundary like this, so it's going to grow forever, not just to above, but to right and left as well. So you can expect negative infinity to positive infinity. Here's a graph, scaled a little bit differently, stretched a little bit horizontally so that you can see this graph a little bit better, but still, same idea. And here's the domain. Set the denominator equal to 0, and you're going to get a negative number inside the square root. This cannot be factored, so you can use quadratic formula, and you get a negative number inside the square root. That can't be real. So there is no real number that makes this denominator equal to 0. So we have the entire real number from negative infinity to positive infinity. One interval corresponding one curved piece. Okay, that was easy. And let's go to the next problem. And come on, this is not really worthy of our class time. It's just a constant function. There you go, duh. Okay, how about the next problem here? Okay, this is gonna be worthy. So please stop the playback and go through with this problem. Alright, did everybody try? Did everybody get the conclusion? Well, okay, let's go back to this Desmos graphing calculator and let's plot it here. The numerator is 2x to the 3rd power plus 3x to the negative 2nd power minus 1 divided by the denominator 3x squared minus 5x minus 2. Did I copy everything here? Okay, alright. Here's the graph. Zoom out, zoom out, zoom out. What do you see? Instead of those predominant horizontal and vertical linear structure, we have this time tilted. Let's compare that with this graph. Yeah, horizontal and vertical. This time tilted. It's a little bit difficult to see from here because I drew it from -5 to +7 only here. Let's go back to Desmos graphing calculator. Okay, in much larger scale, you can clearly see the slanted or tilted asymptotic behavior. But we are going to talk about the asymptotes a bit later. It's a little bit bigger topic, so we're going to talk about asymptotes in sections 2, 3, and 4. For now, let's stick to domains. Okay, let's stick to domains. How many curved pieces do you see? Looks like there are 3 curved pieces. This too confirms that. So, okay, the domain is expected to be negative infinity to some number a, union a to b, union b to positive infinity, like this. That's what I expect. Let's go back to the Desmos graphing calculator. So we have 3 curved pieces, 1, 2, and 3, corresponding 3 intervals, 1, 2, and 3. I got a little bit tired of going back and forth, so let's use this graph. So 3 curved pieces corresponding to 3 intervals. And there should be open intervals because, as you can see, y-coordinate values, the function values, are pushed away toward infinity or negative infinity, not abrupt stop. So the function values are not well defined, so we have to have open intervals, no bracket. As for finding out a and b, well, let's do the same thing as we have done in first problem here, setting the denominator equal to 0, and there you go. Set the denominator equal to 0, factor it, and then you get these 2 roots. So expunging out those 2 numbers, that'll give you a 0 denominator. We can get 3 intervals like this. Just a little of digression here, just a little bit. This factorization from here to there is going to be a little bit tough for some people. If you have no problem, that's great. Stick to your method. But in case there are some students who are a little bit puzzled with this, here it was easy because the leading coefficient is 1. We call this kind of polynomial a monic polynomial. It's monic, so all you need is constant term. Factors of 3 that'll add up to -4, so you get -1 and -3. This is a little bit different. I have to consider both the leading coefficient and the constant term at the same time. How do you do that? One way to do it is a tic-tac-toe method, which I use. So multiply those two. 3 times -2 is -6. So the leading coefficient times the constant. So first number times third number equals -6. And then do the same thing as before. Factors of -6, which will add up to middle coefficient, -5. Okay? First number times third number, get the product, and factor of that product that'll add up to the middle number. What is it? You're going to get -6 times +1. 2 times 3 is 6, but that's no good because you have to get 2 plus 3 equals to 5, so you're going to get same sign. That's not going to give you a -6. So you need 2 different signs, 2 opposite signs. So you need -6 and +1 like this. If you multiply, you're going to get -6. If you add them up, you're going to get -5. And then you can fill out these blanks. Everything is going to be multiplication. This is what you're going to get, multiplication. 3 times -2 is -6. 1 times 1 is 1, horizontally. And vertically, 1 times 3 is 3. 1 times -2 is -2. Everything fits. And then go crisscross. First diagonal, 3, 1. So there you go. And the other diagram, 1, -2. So taking those diagonals, crisscross, you're going to get the complete factorization. This method is called tic-tac-toe method. There are many other methods, but this is the method I usually use. Anyway, I thought it was necessary to review this non-monic trinomial a little bit in case there are some students who are still puzzling. Okay, all right. We get these 2 roots, and then those 2 roots divided the number line into 3 pieces. So we have 3 intervals, -infinity to -1/3, -1/3 to 2, 2 to infinity, 3 intervals that correspond to these 3 curved pieces, 1, 2, and 3. Looks like everything is complete. All good? All good? Agreed? Wrong. There's a mistake. Find out. Stop the playback and find out. There's a mistake. What's wrong here? Found out or did not find out? Okay, here we go. Actually, the graph consists of 4 curved pieces, not 3. Look at this. This is extremely stretched. Horizontally, it goes from -2 to +4, but vertically, it goes to -200 to +150. And look at this curved piece here, down here. Everything is taking place between 0 and -1/3 in terms of x-coordinates, but in terms of y-coordinate, it's beginning from -80 or something. So in naked eye, it's really difficult to see. Let's see. It's really difficult to see what's going on here, but if you really stretch it, like this, then you can see it. There are 4 curved pieces, not 3. So you're going to expect 3 intervals, not, excuse me, you have to expect 4 intervals, not 3. So how do you get those? Well, let's go back to this problem, and we had a solution, and I talked about better solution, and my suggestion was to work out the numerator and denominator at the same time rather than just focusing upon the denominator. This time it was okay to do that because the original problem was simple. This time it's not going to work very well because just denominator, you're going to get only 2 x values, but you need 3. So how do you work it out? Work out the numerator and denominator together at the same time. That's the rule of thumb. Let me expand the font a little bit. So, x to the -2nd power is problematic, so multiply by x squared to both numerator and denominator. And numerator, you have to expand those out, and you get this trinomial, which cannot be factored as a matter of fact. And look at the denominator here. X squared is already out, and what's left here is quadratic, so factor it out, and we get this factorization. So we get 3 factors, and you get 3 x-coordinate values that will make denominator equal to 0. -1/3, +2, yes, but also x equal to 0. So those 3 numbers divide the number line into 4 pieces, so we have 4 intervals like this. A little bit better graph is here. And then the red vertical lines corresponds to the singularity where the denominator hits 0. So this educated guess did not work out this time. Technology is a great tool, but do not worship your calculator, okay? And if you know the underlying mathematics, it's great, but if you do not understand the underlying mathematics, you can fall into this kind of trap. And this kind of trap is everywhere, and if you make this kind of mistake in an exam or something, you lose some points and that's it. But if you do something like that in multi-million-dollar project, then that's going to be a big problem. Okay, so much for a little digression, and let's complete this section. So the domain problems are always important, but for the next 3 sections, we're going to work out asymptotes mostly. Horizontal asymptote like this, or vertical asymptote like those, or slanted asymptote, a little bit exceptional case, and this is really exceptional case, curved asymptote, which I'll never write in the exam, but I'm going to show you some pretty pictures later on. Our textbook author does not consider curved asymptotes for very good reason, too complicated. Okay, so much for section 1, and let's meet again in section 2.